represents SimpleMapping, a real-time visual inertial dense mapping system integrated with deep multiview stereo network. Real-time dense mapping is crucial for mixed reality applications, and it often relies on range sensors like RGB cameras. For instance, Kinect Fusion views all the depth data streamed from a Kinect sensor into a global 3D module in real time, while Bundle Fusion improves pose estimation by considering the entire history of RGB input. More sophisticated methods, such as Vox Fusion, combines traditional TSDF representations with NeRF, neural radiant films. However, these methods can struggle in well-lit outdoor environments and could be greatly affected by objects with low reflectance or transparent surface. As a result, researchers are now exploring RGB-only dense mapping solution. CNN SLAM is considered as one of the pioneering works that use single-view depth predictions from neural networks, but it had limitations such as noisy depth output and high computational demands for optimizing the entire depth map. To overcome this issue, CodeSlam and its derivatives introduced a method using a conditional variational autoencoder to encode dense depth as a latent code, making it more manageable for optimization. However, they didn't consider the dense geometry consistency across multiple views, leading to lower quality reconstructions. In contrast, coupled with multiview stereo networks, Tandem is able to generate finer and more detailed reconstructions. Recently, there is growing interest in using NeRF for scene representation. However, these methods, like NeRF SLAM, are memory-intensive and time-consuming, making them less suitable for real-time systems. Among various RGB methods, integrating visual odometry with multiview stereo stands out as a promising approach for achieving real-time reconstruction. Traditional feature-based visual odometry analyzes image features to determine the robot's pose and maintains a sparse local map. MVSNet initially generates a plane-swift cost volume, then it predicts dense depth for the reference image through cost volume regularization modules. Considering this, an intriguing idea emerges, incorporating the sparse depths obtained from the VIO local map into the multiview stereo. This integration can potentially lead to a more compact, efficient, and robust approach, ultimately resulting in a more accurate dense depth predictions for keyframe in the real-time reconstruction process. Our proposed system begins with feature-based visual-inertial odometry, which leverage monocular images and inertial measurements to achieve pose tracking and local map generation. Here, the example image demonstrates the camera trajectory with the current frame marked in green and the local map with 3D points in red. The gray triangle represents the frustum of the reference camera. To prepare the inputs of the subsequent network, the VIO undergoes keyframe selection and sparse depth sampling. Keyframes are chosen based on criterion such as co-visible connections, relative pose distance thresholds, and defined penalty matrix. These selection criterion strike a balance between the triangulation quality and view frustum overlap. To generate 2D sparse depths, we project 3D map points within the reference frustum onto the image plane. Subsequently, we filter out extreme outliers and less accurate map points, resulting in a collection of 18 to 300 valid sparse points. We utilize the reference image and sparse depth in the single-view depth completion process. This procedure involves passing sparse depth and reference image through sparse depth encoder and RGB encoder respectively. These encoders are composed of step-down sampling VGG blocks with skip connections. The depth decoder then takes the deep features extracted from the both encoder and predicts the depth prior in the last layer. We could observe this depth prior provides a rough description of the object boundaries. The depth prior and the hierarchical feature maps are delivered into the next process. The feature extracted from the chosen keyframe images, coupled with pose estimates and the previous depth prior, together contribute to a creation of a four-dimensional cost volume. Reconstruct the cost volume under the reference camera's coordinates. The depth pair serves as center surface, and then we allocate other depth hypothesis surface at consistent intervals on both sides in parallel to the center one. This construction results in an empty coarse volume with dimensions of D planes by height by width. For each 3D point on the hypothesis surface, we associate it with a corresponding cell in the coarse volume, depicted in orange. Next, we populate the volumetric cells with defined multi-view geometry relations and metadata, including dot products of extracted feature between the reference frame and the wrapped source frames, the features themselves, ring directions extending from the camera center to the 3D point, relative ring angles between cameras, and more. All these features collectively contribute to a feature space with C dimensions. Next, a multi-layer perceptron is implied to reduce it into a three-dimensional coarse volume feature. The MVS2D CNN regularization process integrates hierarchical feature maps from the depth completion into the decoder and predicts the final dense depth. To achieve globally consistent reconstruction, the depth maps are incrementally fused into a truncated signed distance function module. In summary, our system consists of two main components, feature-based visual-inertial odometry and sparse point-aided multi-view stereo network, which can be roughly divided into a single-view depth completion and a multi-view stereo. It's worth highlighting both the depth pair and feature maps from the depth completion play significant roles in the multi-view stereo. Here we show a demo of our system running on a single GPU in real time. For better visualization, we accelerate the demo by 8-folds. Our method displays more accurate depth prediction compared to the other systems. The baseline system denotes the same VIO format integrated with our baseline network, SimpleMapping. Our method excels in predicting detailed structures such as the ladder, chessboard, and chair highlighted in the figure. For 3D reconstruction, our method consistently outperforms current state-of-the-art systems by providing more detailed reconstructions and reducing noise. This improvement is observed even in the challenging scenarios with rapid camera motion and low light conditions, as seen in difficult sequence 203 in the EuRoC dataset. When evaluated on other SLAM dataset, our system demonstrates better results. Both the baseline system and tendon suffer from inconsistent geometry and noticeable noise. Furthermore, we showcase the comparable reconstruction performance of SimpleMapping, utilizing only a monocular camera setup against the SOTA RGBD method. Box fusion tends to produce over-smoothed geometries and experience drift during a long time tracking, resulting in inconsistent structure. Quantitatively, we also surpass competitors' methods with a large margin in terms of 3D reconstruction. We use the metrics from transformer fusion, namely accuracy, completion, recall, and F-score. Our method exhibits a substantial improvement over all the data sequence and achieve excellent performance on the challenging scenarios, while the other methods shows performance drops. When evaluated with monocular camera setup, our proposed system consistently outperforms tendon and exhibits competitive performance to box fusion. We present average per keyframe runtime for each module and per frame runtime for the whole process of tendon and SimpleMapping. Ours can process images at approximately 20 frames per second, exhibits a large margin improvement. Our system can be applied to AR applications with minimum modification. We show here an example of randomly placing objects inside a virtual scene. SimpleMapping shows accurate representation of spatial relations between real and virtual elements. Thanks for watching. Please feel free to ask any question during Q&A.